Okay, so that was the Luce-Yakola random method. And now we will cover something which is called simulated annealing, which is an improved version of the random Luce-Yakola method. And this simulated annealing procedure, it really has similarities with the physical process of heating up something and then letting it cool down. Essentially, this simulated annealing, it's an optimization method which uses the analogy with thermodynamics. Essentially, at high temperatures, molecules, they move quickly and they can move freely. But as the material cools down, the molecules slow down and they tend to concentrate in areas which have the least energy, for instance, okay? So essentially, when crystals start to form, the crystals form because that's the most energy efficient configuration of the molecules, okay? But it takes cooling down for the crystals to essentially find the optimal position, the molecules to find the optimal position in the crystal itself, okay? And that's exactly what the simulated annealing optimization method does. The molecules are our decision variables. We heat up these molecules, we let them move freely, and they will kind of converge to the most energy optimal configuration. And how do we do that is that, again, we generate a random sample. So this is kind of similar to the Luce-Yakola method. And we, of course, move to the new random sample if it improves the solution. So far it's equivalent. But here comes the difference. Sometimes we also allow the procedure to go to a worse point because it helps to escape local optima. And this transition to a worse solution takes place when the temperature is high enough. So as we let the algorithm cool down, at the beginning there is a large probability that we also move to a worse point. But as we progress, as the temperature goes down, the probability by which we also accept a worse solution is decreased. And then what we do is that we gradually decrease the temperature to actually simulate the cooling down of the liquid or of the material. And it can be shown that if the cooling is sufficiently slow, then the global minimum of a non-convex function will be found. Okay? So this is basically the block scheme of such simulated annealing procedure. So what we do is that we randomly generate a point which we think might be the optimum. Then we also have the previous point. Now we compare. Is the new point better than the previous one? If it is, we say this is the new optimal solution, and we generate a new point and again compare and so on. So this is essentially, this pass is what the Luce-Yakola method was doing. It was only accepting a new point if it was better. But the simulating annealing also does sometimes accept a point which is worse than the previous iteration. And to do that, it generates something which is called the probability of acceptance. So in this pass, the candidate, the new point, is worse than the previous one. Okay? However, if the probability is high enough, then we still take it as a new solution. So essentially here it says sometimes we generate a worse solution. So we move essentially in the increase of the function because it helps to avoid local optima. However, if the candidate is worse and the probability is not high enough, then we reject the new candidate. It was the same as in the Luce-Yakola, where we said worse point, decrease the interval. Okay, so that's the path of decreasing the interval. And this plot essentially illustrates the performance of the simulated annealing procedure. That's the function to be maximized in this case. And here what we have seen is the temperature, which kind of reflects the iteration counter in the algorithm. So what we see is that when the temperature is high enough, and let me start it again. When the temperature is high enough, we essentially explore the whole space in kind of random fashion. And we also allow to move to a worse point. However, as we cool down, the system only moves in a small neighborhood of the previous iterations. So this is essentially what simulated annealing is about. To let the temperature serve as a measure for escaping local solutions. If the temperature is high enough, we also explore alternatives. If the temperature goes down, the algorithm is forced to converge. And of course, if we cool down sufficiently slow, then we will find the global optimum. Okay? So how does it work in pseudocode? So it's again an iterative procedure. So we start by some initial solution, x0, and we start with the function value at the initial solution, and this is what we will call is the energy of the point x. Okay? We also have the iteration counter, and we iterate until convergence. What we do first is that we choose the temperature as some function of the number of iterations. We pick a new point in the neighborhood of the previous iteration, and we also evaluate the energy of the new point. And then, if the new point is such that it has large probability of a transition, then we say this will be our new point. And essentially, this simulated annealing method and the performance of these methods depends on the choice of the temperature, neighborhood, and these probability functions. Okay? So let me first show you how this probability function usually looks like. Okay? Essentially, it's a function which is either 1, so we have a probability. Okay? So 0 up to 1. 0 means no transition. 1 means always make a transition. Otherwise, this term, that a random number is smaller than this, essentially means if the probability of transition is large enough, then update the point. Okay? So what do we have here is that E is the energy of the previous iteration. E prime is the energy of the current iteration. We would like to minimize. If we have found a better solution, then we for sure update the solution, because we say the new optimum is equal to the one which we have found in this iteration. However, so essentially the simulated annealing, if the probability would be 1 if we are improving and 0 otherwise, then this procedure would be exactly the Lucy-Akula method. However, what simulated annealing method does it, that it also allows to proclaim the new point as the new optimum if the probability is simply high enough. And to illustrate that, let us take a look at how those functions look like if we plot them as a function of some normalized temperature. So essentially, this is the normalized temperature, and the algorithm, since it's a simulated annealing where we heat up the material and let it cool down, the algorithm starts from temperature equal to 1, and it proceeds until cooling down of the system. Okay? And here we have those functions for different values of this difference here. Essentially, what this means is that if the new point, bless you, is better than the previous point, then there is probability equal to 1, which means there is a certain that we will take the new point as the best so far available solution. However, if the new point is worse than the previous one, it depends by how much is it worse than the previous iteration. If it is only slightly worse, say 0.1, then there is something like still 90% probability that we will go to that slightly worse point initially. However, that's only initially. As we progress with the algorithm, essentially towards the convergence, if the point is just 0.1 worse than the previous iteration, now it's only something like 20% probability that we will go to the new worse point. Okay, so essentially by decreasing these probabilities, what we say is when the temperature is high, let the molecules move freely even to energy levels which are less good than the optimal. And as it cools down, we are decreasing these probabilities. And naturally, these colored lines, they mean that if the new point is very suboptimal compared to the previous iteration, the probability of going to that new point is much smaller than if the suboptimality is much smaller. Okay? So essentially it means that if you imagine that graph that we have seen, this is a point which is far away from the optimum, but sometimes we also allow at the beginning to explore also this point. Okay? Further down the algorithm, the probability of going to a point which is clearly suboptimal is almost zero. Okay? So this is how this function looks like. Okay? And we still need these two rules because we want to say that if we have found a new point, go there for certain. So that's the first kind of the tuning parameter of these simulated annealing methods, how these probability functions should look like. The second one, which is very important for a good performance of simulated annealing, is how this temperature function looks like. Essentially here we have the normalized temperature, but inside of the algorithm we only have the iteration counter. So this function essentially means what is the value of the temperature based on the value of the iteration. And traditionally, in those simulated annealing methods, three choices are usually employed. The first one is that as the iterations counter increases, this expression says that the temperature goes from 1 and essentially decreases in kind of a logarithmic fashion, because we had to let the system cool down. Okay? Another alternative is to start from some known temperature and decrease it by 0.95 to the power of the iteration counter. Okay? So essentially this is kind of the exponential decay, and we can also decay the temperature based on this expression here. Okay? So these are three typical choices for this temperature function, and remember this normalized temperature then enters those probabilistic functions. Okay? So using this pseudocode, you can easily implement your own simulated annealing method, which resembles what's really taking place in thermodynamics. So you are X are the molecules, the neighborhood function simply picks up a new point, so it is a random number from the domain of the function, and you compute the new temperatures and you compute the probabilities. If the probability is large enough, then we make the transition, otherwise we reject the worst point. And you might try to implement the procedure on your own. However, the simulated annealing is so popular in practice that new versions of the optimization toolbox for MATLAB directly include the implementation. It's called simulated annealing bound because it can also take the bounds of the function into consideration. So essentially you provide to it the function handle, which denotes the objective function. You have to provide the initial point and the lower and upper boundaries which you would like the function to satisfy. And as in this case, it would provide you an output like this. Okay, so that was the symbolic representation of the function to be minimized. I'm taking the initial point equal to 2.8, so here it's roughly here. Okay, and we would like the simulated annealing procedure to actually terminate or converge to this point. Okay? And that's exactly what it does. So the optimal X is 1.1529, which is consistent with the global solution. That's the function value, and here we see how many iterations did we require. So for the Lucy-Akola method, there I had something like 300 iterations. This simulated annealing has more iterations, but here the iterations are less important because essentially we have to explore the temperature range from 1 to 0 in the normalized temperatures. Okay, so here it's more about the kind of the physical properties of the cooling down rather than the total number of iterations. And this is the concrete runtime that we required. So with respect to runtime, it might be faster. Okay. And that's the final temperature, and if you look more in the help description, you will find how to choose those cooling profiles, how to choose those probabilities, meaning you can pick the option that's most convenient for the function you would like to optimize. So this is a very nice method because it takes hints from real life. So it's not pure mathematics which says, this is what I think would give me the optimum. This is really taking inspiration from the nature and saying, the nature has already solved the problem of minimization. Like when we talk about the crystals, that's essentially minimization, finding the most energy efficient configuration of molecules. And this is how the nature solves this problem. So simulated annealing is one of the few examples where mathematics means nature. Okay? So the nature tries to mimic, the mathematics tries to mimic what the nature is doing. Okay? And that's why it's so popular, because people understand it. People trust it because they see, okay, nature solved the problem, so if I do what the nature does, I also will solve the problem. Okay? So in summary, what we can say is that it's still a random method. But it's unlike the Lucy-Akola method, which only accepted improvements. Here, we also sometimes accept a worse solution if the temperature is too high, and we do this to escape local optima. Okay? So this improves convergence, and it is a global method because it can be shown again under some conditions that it converges to the global solution. And it has very nice implementation. It is available as a standard part of MATLAB, so you can use it for those tasks you will be facing. Okay. So that's pretty much it for the simulated annealing method.